Thank you very much. It is a great pleasure to be here. So I'm going to talk about some old work and some new work. The new work is joined with Simon Buchholz and should be on archive in a few weeks. Okay? So first I'm going to try and give a bit of a physics motivation about the kind of models that I will talk about. Then I will gently describe how the model works, first in dimension 1, where things are kind of simple to see, and then how things generalize to higher dimensions. I'm going to discuss a bit about the kind of questions that we care about in these models, whether or not we have disorder in them. I'm going to discuss some of the results that we have first in the strictly convex potential case, where we have a lot of tools available. I will also introduce some new results but for non-convex potentials that I have with Simon. Then I'm going to discuss a bit about the model with disorder and how disorder will affect the results that we have from before when we had this disorder. Okay. Okay. So in nature we have lots of physical systems, and we have a macroscopic side of things where we can see what's happening, and what's happening at macroscopic level will influence the behavior at microscopic level, and there's a direct interaction between the microscopic and the macroscopic structure. The kind of systems that I'm going to talk about are interface models. Basically, I care about systems where there is a sort of a phase transition, a separation between different phases. For example, we have water and vapor at 100 degrees, or water and ice. So we have a little separation phase, and that is called an interface. And my favorite way to think of an interface is something like this, yeah? Which is also in itself an interface. Okay, so what we want to do, we want to look at a system. So as Marek also mentioned, at macroscopic level, we may care about shape, the shape that we have of the interface. At microscopic level, we are going to model the system using this Gibbs measure. We are going to model using Gibbs measure. And to give one example that we care about crystals and the way they react to various temperatures and the way they react to deformation. And I'm going to just slowly. So crystals, they are macroscopic objects, yeah, and they have ordered arrangement of atoms and molecules, which are at microscopic scale. And if I am to make a statistical mechanics model of a crystal, I can have these little balls connected by springs. And you can have heat, which can cause the way that the springs interact. Okay? And famous, you can think of it as connected to a famous statistical mechanics model, which is the lattice springs model. And we have configurations of our system. So if I were able to have a camera, and I could take pictures of my systems, I could, for example, take pictures of the atom's position at any given time, and I can take lots and lots of pictures, and this will give me samples of a probability measure on these configurations, and this is the Gibbs measure. And for every configuration, the probability of this configuration, so it's exponential of minus beta times energy of the configuration, and beta is the inverse temperature, so it's 1 over temperature, and it's positive, or sometimes it's 0. Yeah? And one property that we have for such a system, if we were to ignore any external influences, it's that if we move every atom in the same direction by the same amount, should not change this energy, and therefore should not change the probability of the configuration. And this mathematically will mean that I will have to have for my Gibbs measure something called shift invariant. Yeah? So the Gibbs measures should have some sort of shift invariance property. Now, of course, in a very simplistic situation, I can think that the energy between any two atoms is quadratic, which will result in the Gibbs measure being a multidimensional Gaussian. And we will see what things happen for our system when we have multidimensional Gaussian, and then how things change when we replace the Gaussian by something else. So one simple example of an interface is the one for an Ising model, which is not the model I'm going to talk about. So this is a discrete interface case. But just to emphasize that what we want to model is simply the interface, the phase between different states. Yeah? So interface is just a transition region that separates these different phases. And here on this slide, I have a picture of a one-dimensional interface, which I stole this picture from lecture notes of Belenik. Yes, so here what we have, this is just a one-dimensional phase, and the interface is this, and it is it's just this solid line. And what I'm going to start with, I'm going to start with a finite volume system, and then I will push the volume to infinity. Yeah, and in this one-dimensional system, this is my volume. I have the boundary of the system here at minus n and n. So this is I have the boundary of the system. I'm going to define the so-called height variables, which are the configurations, and they are the distance of the interface above or below the line. So these are the phi I. And for most of my talk, these phi I will be in R, but some other people, and I will mention this towards the end of my talk, they also study the case when you have phi I not just in R, they are in R to some Rm for m greater than 1. So one favorite boundary condition that people work with for these systems is the zero boundary condition. So that means at the boundary here, just at minus n minus 1 and n plus 1, I'm going to fix this height variable to be 0. And this is nice because it will allow the integrals that I will introduce later to be finite, and also zero boundary condition is a nice boundary condition. But of course you can fix the boundary also to something else. The energy in this simple case is just the sum of v phi I minus 1, where I goes through all the points of my volume lambda n. And for simplicity here, I'm just going to take v to be the quadratic. Yeah, and we see from here that our Hamiltonian is just a function of the differences of this height variable, so it's of gradient nature, hence the name. Okay, so then next quantity of interest that I will introduce is the finite volume Gibbs measure, and it is just one over the normalizing constants, and then you have exponential minus beta times the Hamiltonian, and then here I have the Lebesgue measure. Yeah? And this is just a multidimensional centered Gaussian measure. Yeah? And beta is the inverse temperature. And for simplicity here, I first took these zero boundary conditions. They are nice because if I don't fix some boundary condition, then my integral will blow up. Yeah, will not be final. Yeah? And as I said, we can replace the zero boundary condition by some other boundary condition psi, and later on we are going to, of course, replace it by some general boundary condition psi. And this will mean that at boundary points, instead of these phi's, I will put psi. Okay, so this is the very simple one-dimensional case, but of course we can do this for any dimension, and then I'm just going to replace this interval by a discrete box, which again has a boundary. So that means that just points which are outside the box, but a distance 1 from the points in the box. Then I can define again the Hamiltonian, it's again the sum of v phi I minus phi j, where ij are nearest neighbors, so they are at distance 1, either inside the box or on the boundary. Yeah, and we can define the corresponding finite volume Gibbs measure for it, same as before, first with zero boundary condition, but then of course we can replace this zero boundary condition by any other boundary condition. And this is a Gaussian measure, and it is the famous Gaussian free field, which has been extensively studied. Okay, and some properties that we have is that if I look at the covariance of these height variables phi x, phi y with respect to this measure, to this Gibbs measure, I end up with a green function, and this we will recall later on when we come back to some of the tools that we use for this kind of models. And of course, Gaussian free field appears in many physical systems, and in 2 dimensions, it has lots of connections to other kind of models, and it has also connections, for example, to SLE, and so it has lots of connections in many directions. And I'm not going to discuss that today. So for now, we just made this the v to be quadratic, but of course we can define such a system, such a Hamiltonian, such a finite volume Gibbs measure. We can define it for more general interactions, for general potential v, and for general boundary conditions. Just the same way, you have 1 over normalizing constant exponential minus beta, and sum of v phi I minus phi j, where ij are either in the box or on the boundary, and are all points at this ij and are distance 1 from each other. And again, so we have the Lebesgue measure, and on the boundary, I'm going to fix phi I to be some finite psi j. Okay. Now, one particular kind of boundary condition that people like and that comes in useful for a lot of characterization is the so-called tilted boundary condition. So basically, I'm just going to fix some u in Rd, and the tilted boundary condition is just something which looks like that. So basically, I'm going to fix this on the boundary instead of just fixing the zero boundary condition. And this, as I said, will be a very useful boundary condition when it comes to characterizing my system when I push the volume to infinity. Now, for the purpose of this talk, I'm going to assume, so we are going to make the technical assumption that v is an even function, and I'm going to also make some additional assumptions. So second derivative is smaller than a constant, and v is greater or equal than a squared plus b, where a is positive. So basically, in some sense, this condition says that I'm not that far away from a quadratic. So I'm not too far away in some sense from the Gaussian free field. So this condition excludes, for example, the phi 4 model. So it's that maybe, for example, Paul Dario talked on Monday, and he the kind of model that he works with. I mean, he works with the kind of results that he has, as far as I understood, based on the looking at the archive paper, would also could potentially include the phi 4 model. But the kind of model I'm going to talk about today, so I'm excluding with these conditions the phi 4 model. So it's basically staying in some region not so far away from the Gaussian. Okay, so I define finite volume Gibbs measure. Another quantity that is of interest is the so-called surface tension or free energy. Yeah, so it's, in some sense, you can think of it as macroscopic of a surface with some tilt u in Rd. And it's just, you take log of the partition function, so of these normalizing constants. So this is the z is just the integral of this quantity, and you take the log in the case when I have this tilted boundary condition. Yeah? a notation that I'm going to use throughout the talk is this grad phi, basically just the difference of the height variable. So the difference when they are nearest neighbor. Okay. So these are the quantities that I will use. Okay. So what kind of questions do we have? So well, some questions we may have first. The first question is, well, if I look at this finite volume surface tension, if I'm going to take the volume to infinity, if I push the volume to cover everything, will the limit exist? So this is the first question to ask. But is there a limit? There's a limiting of this finite volume surface tension. Then you may want to ask, what kind of properties does this limit have if it exists? And the kind of questions that we care about are, is it convex or is it strictly convex? Does it have some sort of regularity? Yeah, so these are the questions that we care about regarding the surface tension. Then, of course, the next question addresses the finite volume Gibbs measure itself. So we want to take some sort of infinite limit object of this. And as Marek explained on Tuesday, this is you can take such limit as long as you have to define the so-called DLR conditions, and then you can try to think whether such a limiting object exists, and under one assumptions on the potential it exists. Once you have a limit, if such a limit exists, then you may want to know whether it is unique or if there are many such limits. Then there are other kind of questions you may care about regarding this limiting Gibbs measure, what kind of how the curve of covariances it has. You may want to care about scaling limits, large deviations, hydrodynamic limits. So there's a lot of questions that you may additionally ask. And the kind of results that we get depend on the kind of potentials that we have. Okay. So I'm going to next talk about the known results that we have for potentials which are uniformly strictly convex. So potentials which are somehow have the same quantitative behavior as the Gaussian free field. Yeah? So this question, we wanted to know whether such a limiting object existed. Yes, and it exists. You can show that this limit exists by some careful subadditivity argument that can be located in the paper of Funaki and Spon. Then next question is it convex? Is it not convex? And you can prove strict convexity. So and you can also prove C2 regularity. So in the paper of Funaki and Spon, it was just T1, but in the more recent work by Armstrong and Yu, so this was improved and a long open problem was solved. Then next question is the question regarding whether these infinite volume, if these Gibbs measures exist. And it turns out that the Gibbs measures do not exist for dimensions 1 and 2. So this is connected to the covariance, to the green function structure in dimension 1 and 2, that it blows up. So they only exist in dimension 3 or higher. So then the next question is, can I define some kind of object such that for which this some sort of infinite volume Gibbs measure will exist in dimension 1 and 2? And it turns out that you can. And you can, so if we, and this is connected to the gradient nature of our models. So if we remember, the Hamiltonian is just a function, is just sum of the v of phi I minus phi j, where these are of gradient nature. So then you can define a gradient Gibbs measure. So you replace this Lebesgue measure by some uniform measure on the gradients, and then things will become nice and finite. And in some sense, it suffices to fix an additional point in order to do that. So basically, so far we just fixed points at the boundary, but in order to achieve some gradient object, which in the limit is finite, it suffices to fix an additional point inside the box. So that is, I'm going to fix, for example, the 0. I'm going to fix the 0 point, and I'm going to fix it, for example, to 0 boundary condition at 0. And when I do that, my green functions will become nicely behaved, and I will be able to have limits for these measures for dimension 1 and 2. And this was noticed in the paper of Funaki and Spohn. It's a really beautiful paper, by the way, and it's my favorite paper in the area. So they call this measure the gradient Gibbs measure, and as I said, this will exist for all dimensions. Now the next question is this measure unique? And well, it turns out it's not. Why is it not? Well, so remember these tilted boundary conditions that we have. Now it turns out for every tilted boundary condition, I will be able to construct one infinite volume gradient Gibbs measure. So for each one of them, I will be able to construct at least one of these. Then the question is, how many can I construct with one tilt, with such a tilted boundary condition? How many infinite volume gradient Gibbs measures can I have for every tilt? And it turns out that there's exactly one of them. So if I fix U in a D, there exists exactly one gradient Gibbs measure, such that when I look at the expectation of these gradients with respect to this measure mu, it is equal to the tilt in that direction. So I look at the difference of the gradient in a particular direction, and this expectation is equal to the tilt in that direction. And exactly one shift invariant gives a Gaussian gradient Gibbs measure with such an expectation. And sometimes I'm going to call this expectation tilt, or expected tilt, and even though it's an expected value. Okay, so for each U, there is exactly one such a Gaussian gradient. Now, of course, the next question that I have is, can I say some other kind of quantitative, can I say some properties about how particles will interact with each other given with respect to such a measure mu? And this results in decay of covariances results, scaling limit results, large deviation results. Okay? So this is a number of properties that people look at with respect to such system. Okay. Now, if I am in the universality class of the Gaussian free field, so if I have this assumption, there are a number of useful tools that people have. One such tool, as Marek also mentioned on Tuesday, is the Braskamlieb inequality. So basically, I'm going to take any finite volume Gibbs measure or gradient Gibbs measure with potential satisfying this property. And if I look at the variance, I have upper and lower bound for it by the corresponding variance, but with respect to a Gaussian free field instead of the one with potential V. And this is very useful because this is what allows us to give, for example, existence of the infinite volume measures in this case. And of course, we have also a more general version of this Braskamlieb inequality. Okay, so for covariances, we have the random walk representation, or the Heffer-Sjöstrand representation. And this was introduced by Deutschel, Jacomin, and Joffe in 2000. And basically, they look at the covariance matrix, and it was in terms of green function of a particular random walk. And using this representation, then you can find covariances for the finite volume objects, both for the gradient model, so for the gradient model and for the original new measure, and also we can go to infinite volume, and infinite volume here, it still stays of order 1 over norm of x minus y to d minus 2, but for the gradient, it improves to constant over x minus y to d. Yes, so this is the properties that we can derive using the random walk representation. There's other tools that we use. So, for example, for uniqueness, you can use the associated SDE. So this is what Funaki and Fon did. Okay, so all of these properties that I have described here, so they rely on some tools that people have in strictly convex or uniformly strictly convex case, and which fail once you move away from convexity. Okay. So then now comes the question: what happens when we have non-convex potential? And you may ask me, well, why do I care about looking at non-convex potentials? And well, first of all, we have a probabilistic motivation. We care about universality class of the Gaussian free field, and we want to know how big is this class. And then there's physics motivation that really, as Marek also mentioned, the strictly convex potentials are not very realistic from the point of view of the physics. And for example, if I look at lattice spring models, a realistic potential has to be non-convex, yeah, to account for the phenomena of fracturing of crystal under stress. We have also the Cauchy-Born rule, for example, when a crystal is subjected to small linear displacement, so the atoms follow this displacement. And this has been studied by various people, Frieseke entirely in 2 dimensions, and they've shown that this Cauchy-Born rule holds for a class of non-convex potentials, and this was generalized by Conti, Dortzmann, Kirchham, and Müller. Okay, so realizing now that it should be a good idea to look at non-convex potentials, let's see what we can do here. The problem for non-convex potentials is that a lot of the tools that we have for uniformly convex potentials, or for convex potentials in general, so they break down, or they haven't been proved so far. However, there are still some results that we have. Now, the Funaki-Spon paper proved that the surface tension was convex regardless whether we were in a uniformly strictly convex potential case or not. So basically, their proof holds under these more general assumptions. So we know that convexity holds. So the only thing now under question is whether it is convex or whether it is uniformly convex. The next question that we have is, well, can we define these gradient Gibbs measures now? Do we have infinite volume gradient Gibbs measures, and do we have infinite volume Gibbs measures? Can we prove something like that? Yes, we can prove them, so we no longer use Braskamp-Lieb inequality, but there are still tools that we have in order to define these quantities. Then we may want to know what kind of tools from the strictly convex case we can adapt. There's a paper by Haria in 2014 where he derived a Braskamp-Lieb inequality in dimension 1. Then there was a paper in 2018 where they looked at the variance under the gradient Gibbs measure in the non-convex case, and under quite in the general assumptions that I listed. Under these general assumptions, yeah, they proved that you have a uniform. So they proved a uniform bound on the variance with respect to the box and with respect to the boundary condition, but the boundary condition was just the tilted one as far as I remember. So it's not it's just tilted boundary condition. Then in the new work with Simon Buchholz, we also have a Braskamrib inequality. And, well, ours is a bit not as impressive because it's a zero boundary condition, and you have it for a mixture of Gaussian. So we have, for all temperatures, we have such a Braskamrib inequality. And we are trying to show that we can extend this Braskamrib inequality to general potentials with this condition. But this is, as I said, still zero boundary condition, so it's maybe not as impressive as one would think. Okay. Then the next kind of result one has, so we want to know whether, so we've seen that we have an infinite volume gradient Gibbs measure. However, in order to get to the kind of result that Funaki and Spohn were getting, so they were showing that there exists one gradient with Gibbs measure which was ergodic, a very important property which they used in the proof. And this is a more delicate issue, so you can show existence of a shift invariant gradient Gibbs measure, but we also have to show the existence of one which is ergodic. And this has been open for a long while for non-convex potential. Now, the way Funaki and Spohn do it, so they use the fact that you have some decay of covariances. You can prove a weaker than this decay of covariances inequality, and they use this a priori to prove that you have an ergodic shift invariant gradient Gibbs measure. And this because we don't have a decay of covariances for non-convex potentials in infinite volume, then this was open. But we can prove that such a, so in this newspaper we can prove that that ergodic gradient Gibbs measures do exist for all temperatures and for all tilts. So far our proof includes this case. We have also other cases of potentials that it holds, but it should be true, and we are trying to prove it for this class of potentials. So it should be possible to show that we have such a ergodic gradient Gibbs measure for this class for this general class of non-convex. Okay, now once you have at least one ergodic gradient Gibbs measure, then you may want to ask about whether it's unique. Yeah? And you may want to ask whether there's other properties. So in a paper by Biskup and Spohn, they proved scaling limit results, and Marek will talk about it. So they proved it for a non-convex potential, which pretty much is of this type as here. Yeah? And for such a potential as here, so a mixture of two Gaussian in non-convex setting, Marek, Biskup with Roman Katecki, they proved that you have at least two infinite volume gradient Gibbs measures which are ergodic and have this expected tilt. So for them, they looked at the case when the tilt was zero, so you had the zero tilt. And they proved that there are two such infinite volume ergodic gradient Gibbs measures with these expectations, but they have different variances. This was proved originally by Biskup and Katecki in 2007, and then Simon has another proof that was published in PTRF in 2001, so last year. Okay, so this one thing to point out, that this is the case when the beta is 1, yeah? So this is so-called moderate temperature regime. Okay. What are the kind of results we have? So in joint work with Jean-Dominique Deuschel and Stefan Müller, and then in another paper with Jean-Dominique Deuschel, so we looked at some non-convex potentials. So we have a convex part plus some non-convex perturbations. So the non-convex perturbation can be quite big, as well as long as it behaves nicely in some LP norm. So it doesn't just have to be L1 norm. We have an explicit quantification of this at smallness in some LP norm, and we proved all results that were known for uniformly strictly convex case. So uniqueness of gradient Gibbs measure with given tilt. We proved decay of covariances, scaling limits. So the same properties that we had for uniformly strictly convex potentials hold or in such a situation. I want to point out that this is the high temperature regime. So because beta is small, is 1 over temperature, so it corresponds to high temperature regime. Now in low temperature regime, there are a number of papers. So the first one was the paper of Adam, Kotetzky, and Müller. So they proved strict convexity and C2 property for the surface tension. So for small temperature and for very small tilt U close to 0. And then there were a number of additional papers so one was by Stefan Adams with Simon Buchholz with Kotetzky and Müller. So they looked at the same question, but this time the height interface. So the height was no longer just in R, so the phi of x was in R to power m. So they extended their result to the high dimensional height variable. And then there also the results of scaling limits and decay of covariances were proved by Susanne Hilger, who's a former student of Stefan Müller. So there's a number of papers. There's 4 or 5 papers in this direction, and they use renormalization group method. So quite different method from the method that we use here. Okay. Another thing I want to briefly point out is that in this paper with Simon, we also look at the decay of covariances, at the scaling limits for this class, for all temperature and for all tilt. And we are again in the universality class of the Gaussian field. So far, from what I've shown you, the only question that the only one of the properties from uniformly strictly convex case that doesn't hold anymore is in the non-convex case is the one of uniqueness. Yes, so uniqueness of shift invariant ergodic Gibbs gradient Gibbs measure. So the uniqueness property fails in certain cases at non-convex potential and at some temperature. So here some moderate temperature. However, a general characterization of the uniqueness is missing so far. Okay. So once I have told you what kind of properties we have when we have models in convex or non-convex setting without disorder, I'm going to add some perturbation to the system, some external perturbation to the system. So, and there are 2 types of perturbations I will add. So the first one is, so to the original Hamiltonian, I'm going to add a disorder of type sum of psi x phi x. So here psi is our IID random variables with finite non-zero second moments. I'm still in the here for the beginning. I'm still in the uniformly strictly convex case because V is still uniformly strictly convex, so it still has the property, same property. Then I can define again finite volume Gibbs measure, same as before. I can define the finite volume surface tension. Things become a bit more delicate because now A shift invariance would fail in infinite volume, so I will have to define something which is shift covariant, which in some sense means that when I take the expectation over the disorder, this measure, then the annealed measure becomes shift invariant. And once I this is the first model. The second model, I'm going to just make the V random. I'm going to say now it's no longer just some fixed function. I'm just going to it's going to have the disorder encoded on it for each bond that we have in the system. And I'm still in the uniformly strictly convex case. I still, apart from that, again, I define the Hamiltonian, I define the gradient Gibbs measure, and I'm interested in the same kind of questions that we had for the models without disorder. So we care about the existence of infinite volume, Gibbs measures, gradient Gibbs measures. We want to know whether there's uniqueness, whether of the measures given some tilts. We want to know the curve covariances, scaling limits, hydrodynamic limits. Okay. So here there are a number of papers. The first one was for the first model, so the model where I just added here the sum of psi. I added this kind of disorder. So in this case, we have somewhat different properties than from the model without disorder. For d equal to, there were no shift covariant gradient Gibbs measures anymore. We could show them we could also show that we didn't have these Gibbs measures for dimension 3 and 4. So this is different from the moment without disorder, where they only didn't exist for dimension 1 and 2, but they did exist from 3 and higher. So here they also don't exist for 3 and 4. However, the gradient ones will exist for 3 from dimension 3 onwards. And not only that, they are unique there's uniqueness of these shift covariant random measures and moreover, when I take the expectation of other disorders, they are ergodic, and these annealed, if I look at I take expectation of other disorder, of the tilts, I recover the same fixed tilt that I had in the Funaki-Schwann condition. Yeah. For the second model, then we can prove this for all dimensions from 1 and 2. Then we also can show, so we also have decay of covariances for the two models. These are things that we can prove. We were able to prove. So I want to point out here that there's also some nice work that was done by Paul Daria with Ron Peled and collaborators, and I'm sorry I didn't get to read it because I was very sick in the last 2 years, but I had a look at the introduction in the last days, and it looks really, really, really nice. So they also look at the models with similar disorder as ours for some other types of potentials, and I think they also consider some different disorder than the one that we have considered, and they look at questions involving decay of covariances. They also look at questions involving how the moments of the model behave. Okay, so briefly, before I end up my talk, I'm just going to come to the title of the talk. So we've seen that if we add disorder to the model and we still stay in the uniformly strictly convex case, then we more or less recover some of the properties of the model without disorder. So the only thing that that disorder was affecting was the existence of the infinite volume gradient Gibbs measure. So in which dimensions it existed. Then we come to the question of uniqueness. How does uniqueness of this gradient Gibbs measure, how is it affected by the presence of disorder. And we were inspired in our work by a very famous paper of Eisenman-Ver in the 1990s. So they looked at a number of models in statistical mechanics, which included the Ising model, and what they showed for dimension 2 is that if you had these models and there was non-uniqueness for the model without disorder, when you added suitable disorder, you got uniqueness of the Gibbs measure in dimension 2. And we wanted to see if we could prove such a property for our model. And for simplicity, let's just look at the model that Biskup and Kotecki looked at. So you just had a model of this type in the Biskup-Kotecki setting, and there you had at least two infinite volume ergodic gradient Gibbs measure with same tilt and different variances. Now we are going to, they had p and 1 minus p. Now we are going to make these p random variables, and when you do that, the non-uniqueness turns out to disappear. So considering, so we have more general potentials than this, but what happens is that when you add suitable disorder in the system, then you will have uniqueness of gradient Gibbs measure. And we have a very loose adaptation of this Eisenman-Ver argument that they developed. I don't want to go into the actual proof till the paper is on arXiv, but basically we combine some specific ideas that from the non-convex models together with an Eisenman-Ver type argument, contradiction argument, in order to show that non-uniqueness disappears, and once you add disorder in the system, you have nice uniqueness even at in such a non-convex setting. Now, some conjectures that I'm going to throw here before I finish. So, conjecture is that uniqueness, so will hold for low enough dimensions, small or equal than some critical dimension. Of course, this is a very wide conjecture because we still don't know, we still don't have a full picture of what happens in the model without disorder. So it's quite a wild conjecture indeed. And then trying to match the behavior of the Eisenman-Ver model, we conjecture that once you pass this critical dimension, there should be the phase transition from uniqueness and uniqueness should shift. So the parameters for which you have uniqueness in the higher dimension should shift. And another question that I'm quite curious about myself is what happens to the surface tension strict convexity once you add disorder in the system. So for models, for non-convex models without disorder, it is conjecture that there will be cases where you have convexity but not strict convexity, that this has not been proved yet. And the question is, what would happen for such models when you introduce disorder? Would you recover strict convexity, or would you still have just convexity of this disordered surface tension? Okay, and before I finish, I would just like to advertise a summer school that I'm organizing with a collaborator, Mircea Petrache. So we're organizing at the end of June a summer school in point configurations, deformations, and rigidity. And we have a number of speakers. So we have Gregor Frieseke, Douglas Hardin, and Edward Saf, and Danilo Radchenko. So they will each give 6 hours lectures, mini courses. We also have some nice plenary talks by Keith Paul, Werner Krauth, Franz Merkel, and Silvia Cerfati. Each of the mini courses will have 4 hours of tutorials. Most of our speakers will be in person, except 1 or 2. We still have funding for the event, so if you know some PhD and postdocs who are interested to come, please let them know of this event. So with this, I will stop here. Thank you very much.